right, this is the last note sheet for Unit 7. It's about growth and decay, which is actually uh, problems that where you could actually use this in the real world. So we're going to talk about growth and decay and several examples here. I'm probably going to do 3 examples and then do a second video because these take a while. So the rate of change in growth and decay problems, the variable y is directly proportional to the value of y. So this goes back to that first lesson where direct proportional is k is some constant of growth or decay. Y and the dy dt is that rate of change. And we are going to solve this and show that when you do a rate of growth and decay, that this dy dx equals ky. We'll simplify to y equals ce to the kt power, and then we're going to use this y equals ce to the kt power to solve some problems. So we're going to go through and do this, show that derivative, show that dy going to be dt because of time. Back here. Okay, so this is going to be dy dt. Is going to equal ky. So we got to separate the y's and the t's. Now k is a number, so we're going to leave it where it is. We're going to divide both sides by y or multiply by 1 over y. Leave the dy here. And then we're going to multiply the dx over here with the k. Now the k is just a number, so I'm going to put the integral symbol in front of that. And I'm going to do the integral of both sides. So this is going to be the natural log of the absolute value of y is going to equal kx plus some c that we don't know what it is for sure. And now we got to get y by itself. So we're going to take e to this power and e to this power over here. I put x. Sorry, this should be a t, and that makes that a t because we're doing dt, not dx. So that's going to give us that y is going to equal e to the kt power plus some c. And just like I showed in other videos, I can make this as e times e to the c power. And then this e to the c power, like other videos, is a brand new c, which we're going to stick in front of the e. So this becomes the exponential growth and decay. So y equals ce to the kt is going to be the growth and decay. Now y is going to be your final amount. C will be your initial amount. K is the rate of growth and change. Now when k is positive, it's growth. When k is negative, it is decay. And anytime you have a natural log between 0 and 1, that is going to be a decay. And whenever natural log is greater than k, it's or greater than 1, it's going to be a growth. So we're going to use that formula on all these problems. So we're going to go through down here, and that's going to be one of the first things we do on all these. So this says the rate of change of y is proportional to k. So again, that is the dy dt equals ky. Now you can go through all those steps we just did, or we can realize that this is going to be this formula. So we got y equals ce to the kt power. Now we are given an initial point right here, 0, 2. So we're going to use that 0, 2 in order to find c. So 2 is y. C stays c because that's what we're looking for. And then we're going to plug 0 in for t. Well, hope we know k times 0 is 0, e to the 0 is 0. So c equals 2. So what this means is on this particular problem, the initial amount is 2. So my equation is going to be y equals 2e to the kt power. Now I need to find k because I don't know what k is. That's why they gave us a second point. We had to use this point, this 0 in here, so that we would get the exponent of e to be 0 so we could find c. But now we're going to use the point 2, 4 and find k. So y is 4 when t is 2. And now we can find k, the rate of change. So I would divide each side by 2 first. Then we're going to have to get the 2k out of the exponent, which means we need a natural log because that undoes e. So these two cancel each other out. So I get 2k is going to equal the natural log of 2. So k is going to equal the natural log of 2 all over 2. Now that would be a positive. So this is a growth chart. I hope you can see over here that that's growing. And then the last thing wants to know, what's y going to be when t is 3? So I'm going to erase this stuff up here. I'm going to plug in all the variables that we know into our original formula now. So we have y equals 2. We found c was 2 a little while ago. E, and now we got k is the natural log of 2 all over 2 t. That's our formula to find all of these values. So this one says we want to find y when t is 3. So we would take, and we're going to plug in three right here. So when I plug that in, this is going to be y equals 2e to the 3/2 power, because that 3 times a half is 3/2, natural log of 2. And then we would probably want to take that 3/2 and move it up to the exponent here. So that's going to be y equals 2e to the natural log of 2 to the 3/2 power. Okay, natural log and e cancel out. So that means this is going to be, I gotta erase some more of this. Like I said, these take a while. That's why I'm going to do 3 now and 3 later. So this is going to be y equals 2 times 2 to the 3/2 power. And then this is 2 to the first, so we are allowed to add those two together. So y is going to equal 2 to the 5/2 power. That would be the answer that we would want for this. And you can use a calculator to write decimal answers. Okay, we're going to go on to the next problem because, again, I've got to watch videos for my classes, and I know I don't like them being very long. Half-life. This half-life, if you've studied, if you've had any chemistry, you probably already talked about half-life before. But half-life is how long it takes different isotopes to decay to half of what they have. So like uranium-236, that's the number, 236U is the name of that one. It takes 4,510,000,000 years for it to decay, and all these other things. It tells you how long it takes to do a half-life. So we're going to use the half-life information on those to solve these problems down here below, at least for this one anyway. So in 1986, Chernobyl had a deal where it had a nuclear accident, and it says suppose 15 grams of this Caesium-137, which takes 30 years for a half-life, was released in 1986 accident, absorbed in the ground. How long will it take for 15 grams to decay to 1 gram? So this is a super long problem. And again, this is going to be y equals CE to the KT power. All right, so at time 0, we had 15 grams. Now I'm going to tell you right now, I know 15 is going to be C because that's the initial amount. But we're going to plug it in and show that C is that anyway. So we're going to get 15 is going to equal CE, and then 0 times K is just 0, so that's 1. So C is 15. So I'm going to rewrite this in here. So right now we have y equals 15 e to the KT power. Now we got to find K because that's the rate of change. Well, up here it says it takes 30 years to get half of that life. So what that means is when t is 30 years, if we started with 15, we would now have 7.5. So we can use that point to find k. So we get 7.5 is going to equal 15e to the 30k power. Now we should take and divide each side by 15, which this is always going to be 0.5 because it's half-life. So that would be half of it there. That's where the 0.5 is. There's half left. Okay, and that's going to be e to the 30k. And then I natural log each side. So this is the natural log of 0.5. If you want to write it as 1/2, you can. And then over here, we have natural log of e is going to cancel out. So we're going to have 3k over here left. 30k, sorry. That's a 30 because I plugged 30 in. And then k is going to equal, and we can divide this whole thing by 30. And this by 30, and that's going to be our answer. You can put 1/30th in front of that if you wish, but there's your k. So your formula is going to be y, which is the amount of isotope there, is going to equal c, which we found to be 15 a minute ago, e to the 1/30th natural log of 0.5, and then times t. Now this question was asking, how long is it going to take to get 1 gram of this stuff left? So we're going to take that equation, and we're going to put 1 in for y, and we're going to set that equal to 15 e to the 1/30th natural log of 0.5, and again, you can make that a half if you want, t. So we got to solve this for t, so we would divide by 15. So divide by 15 here, divide by 15 here. Then we got to take that 1/30th, and we're going to raise that to this 1/15th power, because the natural log is only for that 1/15th. So this becomes 1/30th here. So we move this up to the power of the 0.5. So the e and the natural log will cancel out. So we're going to have 1/15th is going to equal the natural log of 0.5 raised to the 1/30th power. And then that t is just going to be out here by itself. So now we have to divide by the natural log of 0.5 to the 1/30th power. And again, you would take your calculator, and t is going to equal 1/15 divided by the natural log of 0.5 to the 1/30th power. Okay, that would be how you would type that in to get the time. I don't know what the answer is because I'm not taking time to type it down on my calculator. Okay, we got one more problem here that we're going to go down and do. We're going to take a break, and I'll do the rest of these later. So it says, an absent-minded graduate student at the University is studying population of fruit flies. She works under the premise this experimental population of fruit flies increases according to the law of exponential growth. So what that tells me is we're going to use y equals CE to the KT power. She counts 100 flies after the second day. So when T is 2 days, there's 100 fruit flies there. And it says after the second day of the experiment, 300 fruit flies are there after the 4. So we got 4 and 300 fruit flies. On day 4, approximately how many fruit flies were in the original population? Round the fruit flies to the nearest. So C is going to be our value we're going to need for the original. Okay, so we're going to have, the biggest question is we got times 0. What do we get here? So we're going to have to do 2 equations with 2 variables here. So this is a little harder. So we're going to stick 100 in for y. I'm using this first point, and I'm going to stick 2 in for t, and I get that equation right there. And then I'm going to do another equation where I use the other point, and I'm going to get 300. Okay, and that's going to equal, sticking that in for y, CE to the 4k. So I have two variables with two equations. So I need to solve one of these. For C, I'm going to use substitution method. So I'm going to take this one over here and say that C is going to equal 100 over e to the 2k power. So then I'm going to come over here and I'm going to stick that in for C, and that's going to give me 300 is going to equal 100 over e to the 2k times e to the 4k. So I hope we remember that when you have a base to a power, like if I have x to the 5th over x squared, you subtract exponents, so that'd be x to the 3rd. Same thing here, I get to take this 4k minus that 2k. Okay, so this, and I'm going to divide each side by 100, so that's going to give me 3. And then when I subtract those two, I'm going to get e to the 2k, because 4k minus 2k is 2k. Now I natural log each side, so we get the natural log of 3 is going to equal, and when I natural log this e, they cancel out, so this is going to be 2k. So k is going to equal the natural log of 3 over 2. Okay, so now I'm going to take that, and I'm going to plug that back in over here where I solved for C. Plug that back in here. Sorry, back in here for the k. So I'm going to have 10 over e to the 2 times the natural log of 3 over 2 power, because I'm plugging that in for the k. Those 2's will reduce. This is going to be my C. And then e and natural log reduce, so this is going to be 10/3. So what that means is in 3 1/3 days, or 10/3 day, I'm sorry. Nope, C's my original amount. So this is actually going to be a weird number. It's going to say that we started with 3 1/3 fruit flies, but we would use our 10/3 as our initial amount based on what we did with our problem. So that's kind of a weird number to use. So I'm going to stop there for now, and then I'll finish these other 3 later.